Hello students, welcome to today's session. So we are into the third session of the topic of isomerism. We already have placed two sessions, and what exactly is the objective of today's session that I am going to discuss first. The objective of the session is we already have placed this in the session 1, what is isomerism, its definition and the basis of the classification. We classified it into structural and stereoisomerism. In the session 2 we talked about degree of unsaturation, which is quite important, and in the session 2 we also have touched the topic of structural isomerism, in which we have discussed chain and position isomerism. So in today's session we will be discussing these three types of isomerism: functional, metamerism and ring chain. And lastly then because this is one of the most important one, tautomerism, it may take 1 to more sessions to explain this particular topic of tautomerism. So let me directly go into the discussion. We are in today's session, we are going to discuss structural isomerism. In that we are going to target functional, metamerism and ring chain. Those who are joining it first time with me, I just would request you to see at least this session in the last discussion, degree of unsaturation, which is very important, because with the help of this particular topic you are able to understand or able to make the number of structural isomers easily. So let me talk about first the functional isomerism. As the word itself suggests, very easy it is. Functional isomerism is those isomers which would have, of course, same molecular formula, but they have different functional groups. When two or more compounds are cross-examined with each other in terms of isomerism, we shall be saying they would be classified under the category of functional isomerism if they do have different function groups, although their molecular formula is same. Very easy it is, not very difficult one. Just like if I would take the example of C3H6, let me start with this. The degree of unsaturation for this is 1. How do I get it? Because this we have already done 2-3 times in the last 2 sessions. So degree of unsaturation for a given molecular formula is found by this formula. So we are being given C3H6. So the number of carbon atoms are, 3 plus 2, and there is no nitrogen in the formula, no halogen in the formula, only hydrogens. Whatever number of hydrogens are to be there, that has to be subtracted, divided by 2. So degree of unsaturation came out to be 1. Once you get the formula degree of unsaturation from the given molecular formula, degree of unsaturation 1 means that basically degree of unsaturation is the sum of pi bonds and rings in simplest of all way. So this formula which we have found, C3H6, is having a degree of unsaturation 1, which does it mean that it would have 1 pi bond or it may have 1 ring. So once you get the degree of unsaturation, you easily would evaluate that what way it can be made. So if I just would make 3 carbons like this, somebody else can make 3 carbons like this. So the smallest of ring is 3 carbon and 1 ring came into the picture. So the degree of unsaturation happened to came out to be 1 here. And to make the degree of unsaturation in an open chain 1, I just have to place 1 pi bond. Pi bond means wherever you have a double bond, it would have 1 sigma 1 pi, and if you have a triple bond, it would have 1 sigma and 2 pi bonds. So once you get this, now simply you just place the formula to complete the tetravalency of all the carbons. So we end up getting propene here, and here 2 hydrogens, 2 hydrogens, 2 hydrogens. So these two can be said as to be functional isomers, because this is alkene, classified as alkene, and this is cycloalkane. So in many ways they have a different set of chemical reactions, because later on we will be seeing it into. And this particular two things can also be classified here only. I am going to discuss it here only. This may also be said as ring chain isomers. Ring chain isomers, because both of these can be classified under this category because of the fact that here you have a open chain and here you have a cyclic ring. So any two compounds where you have a open and ring, that can be said as to be your ring chain isomers, along with the term functional isomers, because functionally it is alkene and it is cycloalkane. So in that sense you can classify it like this. Moving on to the next example. Next example, we can take it of C5H8. So simply we would find the degree of unsaturation first, because once we get the degree of unsaturation, we would get to know many things about it. So the 5 carbon, 2 into 5, 5 is the number of carbon atoms, plus 2. No halogen or oxygen or nitrogen is there, so 8 is to be minus, 8 is being subtracted, and you happen to get degree of unsaturation as 2. Now once you get the degree of unsaturation 2, just see how many things I can generate from here. So there are 5 carbon atoms. I can draw it like this, 5 carbon atoms, 5 carbon atoms. Someone can draw it like this also. Now see here. Now if I would say degree of unsaturation 2, that means this particular thing can have 2 double bonds, because you need to create 2 pi bonds. 2 pi bonds can be possible in 2 double bonds, and these 2 double bonds can be like this also. Wow, it can be like this also. So here I am not making all the one, I am just showing you these can be the, so all of these what I have just have made, few more can be generated dienes. And 2 pi bonds can also be there in a triple bond. A triple bond can be like this, or simply you can make it like this also, or a triple bond can be like this also, isn't it? So you just, there is no need of checking the hydrogens, it would come out to be the 8 only, because if you stick to the number of carbon atoms are 5. There are 5 carbon atoms in this formula. Carbon atoms are 5 and du is 2, because there are 2 pi bond. Definitely the hydrogen automatically would come out to be 8. So in now here I am going to say it as to be that these are alkynes. This is diene, this is alkyne. So in if I just would compare these two, if I would say, if I have to compare these two or these two or these two, any of these two, we shall be saying these are to be the functional isomers, because on one side I have wrote alkene, on another side we have wrote. So many more can be generated here, because I just have done the things a little speedily. This this can also be possible. And you can also create a one more here, if I do it here only. So this one also can be possible. So now you could have, because degree of unsaturation is 2, so that means it can have 2 rings also. 2 rings also. One ring I already have made. If I just would place one more, so now it has become bicyclo. So bicyclo obviously would have different physical and chemical properties as compared to alkynes or alkadienes. These are said as alkadienes. And this can also be generated like this, 4 carbon atoms in the cyclic ring. Du has to be created as 2, so I just have made 2 rings. Now one more carbon is to be placed. I can place a carbon here, or simply I can do it like this also. This can also be possible. So these are bicyclo compounds where you happen to get 2 rings, and 2 rings can also be generated like this also. So this is spiro. Now this is so interesting. So from the same formula you are able to get so many structural isomers, and all of these structural isomers with respect to each other, if I do it like this or this, these can be said as to be functional isomers, because chemically they are having different set of rings or pi bonds. Fair enough. And here also I can also make one more, in the sense that, just hold on, if I could make a C5H8 into this, if I just would make du is 2, so you can create 1 pi bond and 1 ring also. 1 pi bond, 1 ring also. Just like if I just would say there are 4 carbon atoms, 3 carbon atoms, like this, if I could generate. So here you have one more carbon, du is to be placed as degree of unsaturation here come out to be 1. If I would create one more double bond, it would become 2. Similarly, if I can make this one also, I can make this one also, isn't it? And here in the 3 membered cyclic ring, 2 carbon atoms are more to be added here, and du is to be made 2, because at present du is 1 because of this ring, and now you can create it like this. Wow, so interesting it is. So you can make many structures out of it. So all of these structures, if we just would compare with each other, if we compare them with each other, we shall then be saying it as to be. So what I'm trying to say here is that this compound can be possibly made in the form of alkadiene as a function group. It can be made as alkyne. It can be made as bicyclo. It can be made as a spiro. It can also be made as cycloalkene, which I might have missed this 5-membered ring if I just would make it like this. So du happens to come out to be 5 du come out to be 2 only. Or substituted cycloalkane, substituted alkyl substituted cycloalkane also, or alkene, rather alkene I should say, substituted cycloalkene. Just like if I few minutes back we have just made it like this. So this can also be generated. So all of these would be said to be the functional isomers to each other. I think I made my point clear. So make it a point. So that is why I keep on stressing this fact that degree of unsaturation understanding is very, very important. Now if we go for this C2H6O, now if we simply find du, oxygen is not to be counted in the formula. If you could remember, this is the formula which we have used many times, where no oxygen atom is to be used. So degree of unsaturation came out to be 2 into 2 plus 2 minus 6 divided by 2. It happens to come out to be 0. So this in a way shows that there is no pi bond in this and no ring in it. Now till now, unlike the previous two examples where I talked about C3H6 or C5H8, these had been hydrocarbons. These have been hydrocarbons, and hydrocarbon can be classified into alkane, alkene, alkyne, or cycloalkane, cycloalkenes, or bicyclo, spiro, something like that. Now this is the first time I am picking up a heteroatom here. Oxygen came into the picture. So once you have got the oxygen, now oxygen have the bonding arrangement of two types. Either oxygen can join like this through both sides with single bond, or with one double bond. Now as soon as you happen to get degree of unsaturation is 0, so that means this possibility is omitted. This possibility would not be there. Now what we can do here is, I can simply place it like this, C2H6O. So you just would pick 2 carbon atoms and 1 oxygen, and somebody else can use, because somebody can use the oxygen is in the center. So now if you just would place all the hydrogens here, you would get with the answer, because at present I have wrote du0 for this also, du0, because I haven't placed any pi bond. So here comes the hydrogen 3 to complete the tetravalency, and here comes the H. This is CH3 and CH3. Now as a matter of fact, these would be said as to be functional isomers, because on this side you have alcohol and on this side you have a ether linkage. So ROR is said to be a class of compounds which fall under the category of ether. So we will be saying alcohol and ethers could be classified as to be the functional isomers to each other. Let me take one more example. Just like in this case, if you find the degree of unsaturation here also come out to be 0. So that means this oxygen is being joined to the carbon atoms through single bonds. Now this oxygen can come at the at the center. If I just would place the carbons on this side like this, or something like this, or something like this. Is it okay? So what you basically have generated is, these are all ethers I have generated. And similarly, if I just would place this, and because in all of these I am not writing the number of hydrogen atom, it automatically would come out to be 10 only, because if you kept the carbon atom same, oxygen atom same, and du kept as 0, so the hydrogen automatically would come out to be 10. You can cross check it at your place. Now similarly, if I just would place it here OH, so this becomes alcohol, or you can place it like this also, OH, or you can also do it like this also, or you can place it like this. So almost we have got 7 structural isomers for this formula. But as a matter of fact, here what we are basically doing is, we shall be saying that with respect to each other, all of these ethers and alcohols are functional isomers to each other. So this functional isomerism would be always discussed in respect to each other. When you are comparing two compounds and their molecular formula is same and function group is different, then we will be saying it is a functional isomer. Now the interesting one, now what we have generated, same compound, oxygen is still intact. Here also the formula, the oxygen is there as a heteroatom, but du came out to be 1, because 3 into 2 plus 2 minus 6 upon 2 comes out to be 1. So degree of unsaturation 1 means that this oxygen now can be possibly in this form as well as in this form. But if it is in this form, then that particular structure would have degree, to make the degree of unsaturation 1, it would either be having one pi bond along with it or one ring. Now this becomes very interesting. Is it okay what I am trying to say? If this formula has a oxygen atom written in terms of single bonds, then the other part of the compound must be having one pi bond and one ring, or one ring. Let me show what I am trying to say to you. Now the formula is C3H6O. Now somebody can simply do it like this. 3 carbons you can pick it like this, 3 carbon you can take it like this. Randomly I am writing it. Now since the degree of unsaturation is 1 and you still have to place one oxygen, so I can place one oxygen like this through a double bond or like this. Now once I do this, what basically I have generated, so here to complete the covalency or tetravalency of this, I have to place one hydrogen here, and if I do so, the first entity came out to be propanaldehyde or propanol, or rather I would say it came out to be aldehyde. And similarly, if I do it for this one, this happens to come out to be ketone. Which ketone it is? It is acetone or propanone. So we shall be saying these two are what? These two are functional isomers to each other. But the story doesn't stop here. Somebody else can use it like this also. Somebody can use the oxygen like this and create a double bond here. So now if I would do the bonding aspect here, keeping the placing the hydrogens wherever is required, so this happens to become as to be in what class of compounds it could fall into. It would fall into the category of I will say alkenol. So there is a ene and ol. So this would classified under the category of alkenol. But the story doesn't stop here. Somebody else can use the same entity like this also. If you just would place 3 carbons like this, isn't it? You can place it like this. Here, if you place the 3 carbons like this, degree of unsaturation came out to be 1. But still you have to place one oxygen. So now what you can do is you can place OH like this. So now this happens to be cycloalkanol. This would classified under the category of cycloalkanol. And the story doesn't stop here. You can also create a system like this also. If I just would place 4 carbon atoms, 3 carbon atoms like this, and in between in the cyclic form I just have placed a oxygen here. So here if you would see, du is still the 1 because there is one ring and carbon atoms are 3 and one oxygen atom, so the hydrogen happens to come out to be 6 only. And now this would classified under the category of cyclic ether. So this I have generated a cyclic ether. Which cyclic ether we have generated? I can say it as to be, if I have to pronounce its IUPAC name, it is oxacyclobutane. Although but is not there, but I counted this oxygen as carbon. That is why we have placed a prefix. This is for this particular, you can refer to replacement nomenclature in the nomenclature videos, where I have placed where you would not be using the conventional name, where this prefix is to be used. Oxa, thia, aza, these are classified under the category of replacement nomenclature. Now the point here is C3H6O, what we have concluded, this can be ketone, this can be aldehyde, it can be aldehyde, it can be cyclic ether, it can be a sort of alkenol, or it can be a cycloalcohol, and still I can do many more things. I can place it like this also. If you would just see carefully, just see the number of carbon atoms. Carbon atoms are 3, 1, 2, 3. Degree of unsaturation is 1 because of this pi bond, and 1 oxygen atom is there. So definitely this particular molecule would have the number of carbon atoms as hydrogen atoms as 6. So in what class of compound this would, so this is a alkoxy part, this is alkene. So I can say alkoxy alkene. Alkoxy alkene again may have a same sort of molecular formula derived as is for ketone or aldehyde or for cycloalcohols. Is it okay? So the point here is all of these, but primarily what you basically is being taught most of the time is like this, that aldehydes and ketones are functional isomer, but you have not to rule out other options. These can also be, with respect to each other, they can also be said as to be functional isomers. The story is very interesting and important. Now I just have placed, so here we just have done this one. Now we have added one more heteroatom as oxygen. If you have just placed one more heteroatom as oxygen, here also the Du happens to come out to be 1 only. So there are 2 oxygen atoms. Now what we can do is, I can place it like this. If I just would place the oxygen through double bond, I just have placed oxygen through a double bond and 1 oxygen with OH. So this becomes a carboxylic acid. And similarly, if I do the other thing around it, so this would be said as acid, carboxylic acid, which propanoic acid. And similarly, if I just would place something like this, there is a double bond here and oxygen and this. Again, just mark my point, mark my words. There are 3 carbon atoms. Du is 1 because there is a 1 double bond, and oxygen are 2. So this molecule do have same number of hydrogen as is the previous case. That is, hydrogens would be 6. But this is called as ester. So we can say acid and esters are functional isomers, but other things also could be generated here. Just like if somebody would make 3-membered cyclic ring, 3-membered cyclic ring, Du happens to come out to be 1, and still you have to place 2 more oxygens here. So you can place 2 more oxygens like this also, isn't it? So I can say cyclopropane 1,2-diol, or simply I will say cycloalkanol diol can be said as to be the functional isomer to a carboxylic acid or a ester. So my point here is we can make many things with this formula, and wherever you happen to see different function group with respect to each other, they would be classified under the category of functional isomers. So what I just have said, you can also make it like this also. Now if I just would make it like this, and still you will place 1 OH here. So this is cyclic ether which is substituted with hydroxyl group. So if you just would see, there are 3 carbon atoms, isn't it? There are 3 carbon atoms. And if you just would place 2 oxygen atoms, Du happens to come out to be 1 because of the ring. So here you have 2 hydrogens onto this carbon. Here there is 1 carbon, 1 hydrogen, and here it is 2 hydrogens. So if you happen to calculate the hydrogens, it comes out to be the 6 only. So this way you should have to have this thing in very clear in mind, that when you are being given a formula, you just have to find the Du and try to make as many structures out of it, and in all those structures, if the function groups are different, we will classify them in the category of functional isomers. So in this formula, many more can be generated. Now a simple question, this question has came 3-4 times, once in JEE mains and 2 times in NEET examination. So they have given you this formula C4H8O2. Just develop this habit to find the Du first. So 2 into 4 plus 2 minus 8 upon 2. So degree of unsaturation came out to be 1. And they are saying you have to make all the possible acids and esters. Now we know for sure acid and esters have one thing common, that both of these would have this carbonyl group. and because of this carbonyl group, Du happens to come out to be 1. So what we can do here is, we know that the carboxylic acid always will be a corner group. It is always a corner group. So since it is always a corner group, I just would randomly make all of these like this. And ester is a non-terminal group, so it would be shown it like this. This is the best way. While making the things, you just would make all these structures first in this way, and then keep on adding carbon around it. Now what we can do here is, so in the first one, if I just only 4 carbons is to be placed, 1 carbon is already there in the carboxylic acid, so I can place 3 carbons like this. I can place 3 carbons like this, isn't it? And as a carboxylic acid, more cannot be generated. So these are the 2 carboxylic acids which we have generated. One is butanoic acid, and second is 2-methyl propanoic acid, 3-methyl propanoic acid. If I could rub this, so this is 1, 2, 3. So it is 2-methyl propanoic acid. Now as regard to the ester, now coming on to the ester part. Ester part can easily be made like this. So if I just would place 2 carbons on this side, 1 carbon on this side, and similarly now just keep swapping the carbons. Now I can place 1 carbon on this side, 2 carbons on this side. This way you would not get any confusion, nor you would get any mistake while calculating the, so just make the function group first and then keep on adding carbons on both sides. And very soon we will be saying these will be also classified under the category of metamers also. Very soon we will be doing this. Now what else you can generate? So you can place 1 hydrogen. Now place the 3 carbons on this side. Then you can do another proposals like this. So these are the 4 esters you can create. So the answer to this question would be 6. So you would have 2 carboxylic acid and 4 esters developed from this particular formula. So this is very, very important. Now coming on to the topic of, I think I made my point clear that what basically you have to remember as a functional group, whatever molecular formula is being given to you, just write its degree of unsaturation and try to make as many structures in a different arrangements. If those different arrangement would show you some different function groups, so that would classify it under the category of functional isomerism, rather than mugging it like this, that carboxylic acids and esters are functional isomers. But if in the paper the examiner do little bit of twist and turn, then you get stuck with. So it is better to go the way I have explained it to you. Now coming on to the topic of metamerism, it is again a very easy way of understanding. Metamers or metamerism would come into picture whenever you have with you some non-terminal function group. What is non-terminal function group? Like ether, thioether, ketone, or ester, or secondary amine. Whenever you have a functional group which is a function group of a type of non-terminal, and around this non-terminal function group, if you keep on changing the nature of alkyl group, because on both sides you have some alkyl group, if this alkyl groups are being changed, whatever those structures then you would get would classify under the category of metamerism. So when the nature of alkyl groups are changed around a non-terminal function group, this is an important point, non-terminal function group, the compounds so received are called as metamers. But one thing is very important, metamers must be from same homologous series. I will explain it what I am trying to say in a minute's time, that why this point is very, very important. Let's first do the simple thing. Just like in this question, we just have concluded this question where I have generated these as the all possible esters for this formula. So these would be called as to be metamers. If I would write it, these would be said as metamers. Let me explain once again what I just have spoken about. Let me take this example once again with you. So if I have C4H8O8, and if I would say, or if I have to draw all possible esters for this. So what we have said, ester is having this function group, This is the function group which you always would have with a ester. And around this ester, if you keep on changing the nature of alkyl group, let's say I started like this, there is 3 carbon, here is 1 carbon. Here I do also want to explain that esters are the class of compounds whose nomenclature is always very confusing. Esters are the class of compounds in which 2 time alk is coming. So it is alkyl. Now make it a point the color combination which I am using. Alk in OH. So you are able to see in the IUPAC naming, in the case of esters, 2 time alk is coming. 2 time alk is coming. And this alk is disjoined through the carbonyl CO group and this oxygen. So what I'm trying to say, this is the function group on, and this carbon chain 1 2 3 whatever it is, and one chain is on this side 1 2 3. So this becomes the part of alkyl, and this part would become the part of alkanoate. So this you always have to remember. So I think I made my point clear. So this nomenclature at times is very confusing for a child. Now see here what I can do along with. So this is CH3, CH2, CH2, CH3. Okay, let us first make all the possible metamers of it and then do the nomenclature as well. So one is this. Second is, if I just would place 2 carbons on this side. Now what else you can do? 1 carbon on this side, and you still have to place 3 carbons. I think I made this point wrong. So 3 carbon, this has become 5. No, this would not be right one. Let me write it once again. So we have 4 carbons. So I think I have taken wrong one here also. So this is to be omitted. So I have taken 1 extra carbon here. So okay, now the point here is, here you have 3 carbon on this side, 1 on this side. Now you can place it like this. You just would place 1 carbon on this side and 2 carbons on this side. So this do make a isomer of this formula. And now what you are basically doing is, you are changing the nature of alkyl group. Here this is the function group around which you are changing the nature of alkyl group. What I am trying to say here, the first on this side there was ethyl, there was methyl. Here now you have methyl, and on this side you have ethyl. Now what else you can still would create? Keep 1 hydrogen here and bring this. So this again is a ester, and now you can do it like this also. So all of these which we have generated, we will be saying these as to be metamers. Metamers are the class of compounds in which around the functional group, non-terminal function group, we are changing the nature of alkyl group. Now hurriedly we will do the nomenclature as well. So as regard to the nomenclature, this is the longest carbon chain, 1 2 3. 3 means it is alk, and this alk did not have any double or triple bond, so it is ane, and it is supposed to be written as O8. Wherever it is O8, you have to bring in alk part at the start. So this is methyl, so here it would become methyl. In a hurry, its alk has to be changed into the name. So alk is prop, so it becomes methyl propanoate. Similarly, if I would go for this one, longest carbon chain is this 1 2 3 1 2. So 1 2 means eth, single bonds, ane, and it is to be written as O8, and on this side you have ethyl, so it becomes ethyl ethanoate. Now this is the alkyl part, and this is the only 1 carbon is left in the main carbon chain. So this becomes meth, and all are single bonds, meth in O8, and on the start this is N-propyl. So this is N-propyl methanoate. And similarly, if I would go for the last one, again it is meth, 1 carbon, ane, and you have O8, and on this side you are left with this part is isopropyl. So isopropyl methanoate. So these would be classified as metamers to each other. Similarly, if I would say that draw the all possible metamers for hexanone 2. So this is a ketone. This is a ketone for which the Du happens to come out to be 1, because of the CO group. Now what you basically have to draw is you just would write first the CO group at the center and keep changing the nature of alkyl group. Just see the way I am going to do. So what I am going to do is I randomly would write few CO groups like this first, so that there would not be any confusion. I just have wrote all these ones for you. Now what I am going to do, here you have 4 carbon atoms, here you have methyl. So on this side I kept methyl as such, let's say, and try to see if I could create more isomers, if I would change the nature of these 4 carbonate in such a way that its IUPAC name and nature get changed. So what I can do here is I can place 3 like this, 3 carbon and 1 on the top. Similarly I can do it like this also. Now what else I can do is I can do it like this also, isn't it? 4 carbons. I think only 3 forms I can generate from this. So this basically, always you have to remember this, what we have written is C4H9 dash. This is butyl radical, and butyl radical can have 4 options or 4 ways of writing it. One is you just would have straight chain like this, or second option you can have like this, third option you can have of the type this one, and the fourth option you can generate is something like this one. So basically if I just would place all the hydrogens along with it like this, so this is an important radical which you always have to remember. This is CH2 and here you have CH3, CH3, CH3. So these two are basically being derived from butane. If you have butane, because radicals are derived when you remove one hydrogen theoretically from alkane. So I just have removed theoretically one hydrogen. From where I have removed? If I have removed from here, from that is from this point, this would give me N-butyl. And if I have removed it from this point, then I shall be getting secondary butyl. This is called commonly secondary butyl, because it is the secondary carbon from where I have removed one radical. And this formula can also be written in like this form. That is what you call it as isobutane. Isobutane also would give you 2 radicals. So one is, if you remove it from this point, then it is called as isobutyl. And this particular, if you remove it from here, so this would be called as tertiary butyl. So these 4 radical you can generate from C4H9. That is quite evident here also. This is the C4H9 for which I just have. So these all what we have generated are called as metamers to each other at this point of time, whatever we have made. Now still we have left with few more options. Now what I can do here is, now instead of one carbon, this was methyl. In all of these this was methyl. Now I can make it as ethyl and see if I could generate more. So if I just have made this ethyl, then this 4 carbon chain would change to 3 carbon. So 3 carbon I can place it like this, 1, 2, and the third one, 1, 2, 3. And now you can also generate it like this also, isn't it? I think I made my point very clear. So the point here is, now this is N-propyl, this is ethyl. So if I commonly have to write its name, it is N-propyl ethyl ether. And if you have to write for this, ethyl isopropyl, not ether, ketone, ethyl isopropyl ketone. Similarly, if you have to create more out of it, you have to just see, if I would make on this side more carbon atoms, if I would make 3, now on this side you are now left with 2. So now this got repeated with this one. These got repeated. And I think no more can be generated out of it now. So the point here is that we almost have made all the metamers of the formula. Draw possible metamers of hexanon 2. So these could be the possible metamers of this. Now another one which many of the students do ask me, so why we haven't used this one? If I would make CO at the first position, here it is in the second position, and if you would make it on the first position, if I would make it in the first position, this becomes a aldehyde. This becomes a aldehyde. No doubt this particular formula with du1 and carbon atom 6 definitely would be a isomer of this formula, but it would not be metamer, because now this would be said as functional isomer. That is why I said while making metamers you have to keep the homologous series same. Homologous series has to be kept same for making the metamers. Now let us do few more. Draw all possible metamers for phenitol. Phenitol is this compound, and this phenitol, this is the compound which is being given to us. This is phenitol. Now what else we can generate? If I keep the benzoid ring intact, randomly make few benzene rings like this, and then just keep on changing the position of, so now see what I can do. So if I would make it as so and bring one methyl here, so this becomes 2-methyl anisole. 2-methyl anisole. So that these two then would be said as metamers, because around the non-terminal function group you have just changed the nature of function group, nature of alkyl group. Similarly, if I would make it for this one, so this is 2-methyl, now you can say it as 3-methyl, or you can say it as orthomethyl anisole. This becomes metamethyl anisole, and then you can also generate it like this also, isn't it? So these, and now still you could make one more like this also, methyl benzyl ether. This also could be generated like this. So this is the way which I am telling you that keep the du same while making all structural isomers, and in term of metamers, when you have to make it, you have to change the nature of alkyl group around the non-terminal function group. Now let us do one more question out of this. Which of the following is not a metamer of N-methyl butane 1-amine? So first we have to write N-methyl butane 1-amine. N-methyl butane 1-amine. First we have to draw it. So amine means NH2. So butane means 4 carbon atoms. So you have to draw the 4 carbon atoms like this. Is it okay? So these are the 4 carbon atoms which I just have drawn. These are the 4 carbon atoms, but they are saying N-methyl. So one of the hydrogen of amine is substituted with methyl. So this is the compound which they are asking for. For this you have to just see how many, what they have asked. Which of the following is not metamer of this? Which out of this is not metamer? So the formula which we have generated, or the this is the compound they are asking, isn't it? N-methyl, and this is butane 1-amine. This is the compound, and obviously here what you have to see here is that for this du happens to be 0. There is no pi bond or ring here. So if there is no pi bond ring here, we could see that all of these structures do not have that thing. So the point here is you have these as to be taken as carbon atoms. So these are the 3 carbon atoms. How many carbon atoms do we have? 1, 2, 3, 4, 5. So this is not a metamer, because it is not a isomer in fact, because the point here is it is 5 membered, 5 carbon atoms, 1, 2, 3, 4, 5. Here also it is 5, so it is perfectly right. This could be said as metamer, because you just have shifted 1 methyl onto this side. And similarly, if I would see 1, 2, 3, 4, and this one is 5 carbon atom, secondary amine, it is still intact, and du is 0, so it is also a metamer. So 1, 2, 3, 4, 5, it is still metamer. 1, 2, 3, 4, 5, it is still metamer. But the point here is this particular amine is a tertiary amine, so the homologous series would get changed. the function group, if whatever you are comparing, that function group is to be retained as such while making metamers. That is very, very important. So here the point is, this has become, although this is a isomer, if I would say what type of isomers these would be functional isomer. This is secondary, this is tertiary amine. So when you are making metamers of a given compound, its function group in all those metamers would have to be remain same. So this is the point. So which of the following is not? So the answer to this question would be D option. D would not be the metamer of this particular compound. Okay, fair enough. Let us take one more example. This we have already done, I think so. Which of the following is or are metamer? So this is more than one choice type of a question. Isopropyl formate. So formate is this part. If I just would write, if I just would write it like this, this part, if I just would say, this is the formate part. This is the formate part. So this is formate. Isopropyl means this is isopropyl. Isopropyl formate. For this particular compound, you have to see the metamers. So very simply, I can do, you have to bring one carbon on this side, then second carbon on this side, and this way you keep on making the metamers. So here what you are able to see in the first option, if I would compare it, so this is C3 with one oxygen and Du1. No need of counting the hydrogens. So the point here is, you have 3 carbons, rather 4 carbons. Yes, here you have 4 carbons. I wrote it wrong. Here you have 4 carbons, 3 from the isopropyl, 1 from the carbonyl group. So it is C4. C4, let me write the hydrogens as well. So this is C4H8O2. So C4H8O2. So this compound is a metamer, no doubt about it. And this also, this is the same compound. This is the same. These are same. They just have made the same. So this would not be the answer. And what about this one? 1, 2, 3, 4. So this is also a metamer. But this is not a metamer. Although the molecular formula is same. You have Du1, oxygen 2, carbon atoms 4. 1, 2, 3, 4. So 4 carbon atoms, hydrogens are 8, oxygen is 2. But this is alkoxyketone. Alkoxyketone, because now the function group got changed, so it would not be classified under the category of metamers. So the answer to this question had been A and C option would be said as to be metamers of isopropyl formate, because B option is exactly the same which they have given, so we would not consider that as to be metamer. So I think metamerism is very clear. So while making metamers, you have to keep in mind, you have to change the nature of alkyl group around the non-terminal function group, and while making the different forms of metamers, function group is not to be changed. The function group, if they are ether is in all the metamers, ether should be reflected. If it is ketone, it would be reflected in all ketones. Just like in this case, it is ester, but it is alkoxyketone, which would not be the answer for this particular type of a question. Now coming on to the last part, which is quite easy, ring chain isomers. Molecular formula would be same, but they would have different cyclic and acyclic structures. But while making the ring chain isomer, out of the ring chain isomer, one structure should be open chain, another would be cyclic. Just we have given lot many examples to you. C3H6, this is the first case which we have started with. So this is propene, Du is 1, and here you have cyclopropane. So these would be said as ring chain isomers. Similarly, if I would write C4H6, Du here is 2. So if I just would write diene or something like this, compared with this one or compared with this one, so these would be said as ring chain isomers. Ring chain isomers. So make it a point while making the ring chain isomers. Now here you always have to keep it in mind. Say for example, if I write C4H8, now C4H8 can be drawn it like this, 3 carbon. So Du here is 1. So I can draw it like this. So already I had just created a Du1. Still have to place one more carbon. So this is one structure I can create here. So I can now make it a 4-membered ring. 4-membered ring. Then I can generate it like this or something like this. So now these can be compared or can be said as to be ring chain isomers to each other. So make it a point. You have to keep it in a point that while comparing ring chain isomer, one open chain and ring structure should be there in the system. So this is in regard to the discussion of today's session. We talked about functional isomerism in today's session, functional isomerism, then we talked about metamerism, and lastly ring chain isomerism. So hope to see you in the next session, where the very important discussion would come on to the topic of tautomerism. This would take a lot of time. Thanks a lot. Have a nice day. Stay safe and take good care of yourselves.